Good morning everyone. My name is Mrudula, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today I am going to discuss a topic about KVAR calculations from the subject Industrial Electrical System. These are the contents which I am going to discuss today, like what is power factor, what are the causes for the power factor and how to correct it, what is KVAR correction and what are the benefits and causes for the low power factor. The definition about the power factor. Power factor is nothing but the ratio between the power to the apparent power. Means power factor is the ratio of actual power to the apparent power. Here you can see the formula, that is power factor is equal to kW by kVA. This kW is nothing but kilowatt and kVA is nothing but kilovolt ampere. kW is kilowatt and kVA is kilovolt ampere. So power factor is the ratio of this. Kilowatt is the measurement of actual power, or you can say it as real power, to the ratio of this one is apparent power. So the actual power is measured in kilowatts and apparent power is measured in kilovolt ampere. Both are different forms of power in AC case. Now the power factor definition is the ratio of actual power to the apparent power and the formula is kilowatt by kVA, kilovolt ampere. For purely resistive load, the power factor is always unity. When the load is resistive load, the power factor will be always equal to 1, that is unity. The average power in a circuit is called as the active power and the power that supplies the stored energy in reactive elements is called as the reactive power. Means the power which is being sent from the source to the load is the active power and the return back amount of power which is sent back again is nothing but the reactive power. So, we will be having active as well as reactive powers both in case of AC. Active power. Active power is also known as I said, it is also known as real power or simply you can call it as power. Active power is the rate of producing or transferring or using the electrical energy. That is the usage of electric energy. The energy which is being consumed by the load is nothing but your active power. It is measured in watts and mostly in kilowatts, or often you can call it as kW or MW. kW is kilowatts and MW is megawatts, that is 10 power 6 times of watts. So the term active or real power is used in place of the term power alone. Instead of power alone, we will be using the real and as well as the active power here. Next one is apparent power. Apparent power, this is the product of voltage as well as current. The product of voltage as well as current is nothing but your apparent power. That is why the unit of this one is kVA, that is volt and ampere. Volt as well as ampere. It comprises of both active as well as reactive power and it is measured in volt ampere or often in kilovolt ampere or megavolt ampere. Power factor definition. Most of the loads which we are using are inductive loads. In inductive loads, Like you can take an example of an AC motor or an induction motor. The load is nothing but the inductive load, where the current lags the voltage. Because of that, the power factor reduces. Because of this, the power factor reduces in the case of inductive load. In previous slide, we have seen for resistive load, the power factor is unity, that is 1. But for inductive load, the power factor reduces from 1 to around 0.7 or 0.8. So what happens if the power factor reduces? Here you can see the inductive load cause the current to lag behind the voltage. That is, the current lags behind the voltage. The waveforms of voltage and current are the out of phase in that case. That means if you can see sinusoidal waveform, if this is the waveform of the voltage, the current lags behind the voltage. This will be your voltage waveform and this will be your current waveform, and this is nothing but the lagging case. The more out of phase they become, the lower the power factor value. Means this lagging angle is nothing but the phi. If the lagging angle increases, the power factor reduces, because power factor is nothing but the cos phi, cos of angle between the voltage as well as the current. If the voltage and current are in phase, that means there is no lagging, so the phi angle will be 0 and the power factor will be unity, because cos 0 is nothing but 1. What are the causes of low power factor? The poor power factor can be a result of either a significant phase difference between the voltage and current at the load terminals because of the inductive loads, or it can be due to the high harmonic content. If the harmonic content increases, then also the power factor reduces. The harmonics, you can also call it as distortion or discontinuous current waveform. The load current phase angle is generally the result of poor load current or phase angle. That means if the load current is poor, the phase difference increases and the power factor reduces. Here you can see different types of loads, different type of inductive loads. That is, kinds of inductive loads like power transformer or the lighting ballast or the welding machines or induction furnace or the induction generators like windmill generators, and high intensity discharge lightning also uses, and these all are the examples of inductive load where the current lags behind the voltage and the power factor is less than 1. What are the different other causes? Like distortion of current waveform can be a result of rectifier variable speed drive. Means the rectifier is connected for converting the AC into DC, and this rectifier is also being affected with change in the power factor. Power factor correction. How the power factor can be corrected? That is, the power factor decreases with the installation of non-resistive loads such as inductive loads, transformers, like previous all examples of inductive loads. Because of this inductive loads, the power factor decreases, and the power factor can be corrected by using a capacitor. Why? Because the inductive load, in inductive load, the current lags behind the voltage. But in case of capacitive load, if this is the voltage waveform, the current leads the voltage waveform. That means here also an angle is there 5, but the current leads the voltage. So in inductive load, where the current lags the voltage, that lagging is being compensated by connecting a capacitor in parallel to it, so that this leading as well as this lagging, this combination makes the power factor to be almost equal to unity, that is 1. So to make the power factor to unity or 1, we are connecting a capacitor in parallel with the load in order to make power factor as 1. So these are the, here you can see, these are the rated electrical units called as VAR or KVAR, that is kilovolt ampere reactance. 1 VAR is equivalent to 1 volt reactive power. Okay, so the reactive power is usually measured in thousands, that is K, 10 power 3. K is nothing but 10 power 3. And the capacitor KVAR rating, here also you can see the K value, that is 10 power 3. VAR is nothing but volt ampere reactance, which shows how much reactive power the capacitor will supply. So each unit of the capacitor KVAR will decrease the inductive reactive power demand. By connecting the capacitor, we are decreasing the inductive reactive power demand. Power factor correction, like most of the loads, as I said, they fall into one of the 3 categories, that is resistive load or inductive load or capacitive load. Only the loads can be categorized into 3 types, that is resistive, inductive or capacitor. In most of the plants, the most common and likely load is nothing but the inductive load. Typical examples are like transformer, fluorescent lighting as well as AC induction motor. These are the mostly used loads and they are inductive loads. An inductive load requires 2 kinds of power to operate, that is active power as well as reactive power. As I said previously, active power is measured in kilowatts and reactive power is measured in kilovolt ampere reactance. So to energize the magnetic field, the operating power factor from the distribution system is composed of both active as well as reactive powers. The power factor correction. The amount of power factor KVAR required to correct a system to a desired power factor level is the difference between the amount of KVAR in the uncorrected system as well as the amount of desired KVAR in the corrected system. That means the actual amount of KVAR produced and the compensated KVAR which we are giving by using a capacitor. So the most of the efficient location for the power factor correction by using these capacitors is near the load. That means the loads are as I said, they are inductive loads. So the inductive loads are producing a reactive power. In order to compensate this reactive power, we are placing the capacitors in parallel to this, and these capacitors are mostly placed near the load. So the location of the capacitors are near the load. The capacitors work from the point of installation back to the generation source. That means if we are connecting the capacitors near the load, they will have their effect near the generating source also. So once we have connected the capacitors near the load, the effect will be in the transmission line as well as in the generating stations also by connecting this capacitor near the load. The individual motor correction is not always practical. Sometimes it is more practical to connect larger capacitors, on the distribution bus. During the distribution also, we need to sometimes connect the capacitor banks. That is, when more number of capacitors are connected in connected in parallel, you will call it as capacitor banks. This is an example of a capacitor banks where 3 capacitors are being connected in parallel. So sometimes if the load is very low, small load, we can compensate by using a single capacitor. But when the load is high, we need to connect more number of capacitors, that is capacitor bank, in order to compensate the reactive power. KVAR correction. So KVAR correction is done by using the capacitive, that is capacitive power factor correction is being applied in the electrical circuits as a means for minimizing the inductive component of the current and thereby reducing the total losses in the supply. So the introduction of power factor correction capacitors is widely recognized method of reducing the electrical load. So thus, by minimizing the wasted energy and hence increasing or improving the efficiency of a plant and reducing the electricity bill. That means if the power factor is being improved, the losses are going to be reduced and the electricity bill is also going to be reduced. It is not usually necessary to reach the unity. That means we always try to make the power factor as unity or 1, but that may not be possible. The power factor will be mostly around 0.95 to 0.98. That means we will try, but we cannot reach mostly the unity power factor. But 0.95 and 0.98 power factor is also a good amount of power factor. This is being attained by using or installing suitably sized switch capacitors. That means a switch is also being connected to this capacitor banks. Means based on the load, that is if it is a half load or a full load or 3/4 load. So based on the load, we can switch these capacitors. We can reduce as well as increase these capacitor in this capacitor bank based on the load which is being connected. Here is a diagram, triangle. This triangle is nothing but which shows the active power, reactive power as well as the apparent power, and the angle, this is nothing but the angle cos theta, which is nothing but your power factor. So here you can see KVA, that is apparent power, is equal to square root of kilowatt square plus KVAR square. This is nothing but the real power, this is nothing but the reactive power, and this is the apparent power. That is combination of real as well as reactive power. Here are some of the examples of equipment. That is, lightly load inductive motor will be having a power factor of 0.2 and highly loaded inductive motor will be having around 0.8. Fluorescent lighting, neon or fluorescent lighting will be having around 0.3 to 0.7 power factor, and incandescent lamp. This is nothing but an example of resistive load. This is the example of resistive load. So that is why it is power factor is unity. So all the types of resistive heat, like examples are like toaster, space heater, hot water element as well as stoves are having a unity power factor, that is 1. As I said previously, the problem is the inductive load because the power factor reduces. As the power factor reduces, the electricity bill increases as well as the losses also increases. What is this? KVAR is, or at the rate EC, is nothing but electric compensation. That is, to improve the power factor, we are being compensating, or we are connecting different types of compensators to the load in order to improve the power factor and reduce the reactive power content in the apparent power. What are the benefits of this? By reducing, it reduces the harmful effects from the EMFs, that is electromotive force, as well as the less power system losses. That means the losses are reduced and harmful effects are being reduced, and heat and permanent failure. When the motor runs with more reactive power, the motor will get heated up and it may get damaged. So this damage also reduces, and motor runs with cooler effect and more efficient and increases its life expectancy also. So we can increase the lifespan or the life expectancy of a motor by connecting these compensators, and it also increases the starting torque and reduces the maintenance cost also. So all these things ultimately leads to the reduction in the electricity bill to the consumer as well as for the generating stations also. Causes for the low power factor. What are the different power factors? As I said, because of the inductive loads. Because of the inductive loads, or because of the harmonics. Because of the harmonics also the power factor reduces. Next topic. These are the different ways how the power factor is being reduced and what are the effects of reduction in the power factor. In next class, I would like to discuss about the different types of compensations for improving the power factor. Thank you.